Aim. To determine the Young's modulus of elasticity of any material of a given wire using Searle's apparatus. Before we perform this experiment, first we need to know is what is Young's modulus. It is a physical property that measures the tensile stiffness of a solid material. It shows the relationship between tensile stress and axial strain. In other words, we can say that it is the measure of how easily the material can be bended or stretched. Now we will understand the concept of this experiment. As you can see on the screen, there is some kind of wire or rod of length L. When we will stretch this wire, there will be some increase in its length due to the force applied, which we will say is delta L. A restoring force will be generated by the body to get back in its normal form. The whole process will give us two new physical quantities. One of them is stress, which is the restoring force produced by the body per unit area, while another is strain. It is the ratio of change in length to the actual length of the material, or relative change in length. It shows us how the material has been deformed on applying the force. If we want to increase the strain, or say increase the length of the body, we have to stretch it more. This will increase the stress, as if you deform the body more, it will try to snap back even more. We can say that stress and strain both are dependent on each other and they are linearly proportional to each other. Now we proceed to the theory part of the experiment. As you can see, this is the setup of Searle's apparatus given. You can just pause the video and read it. I'll explain in short. Basically, we have to deal with two types of wire. They are of same material and same length. One is a reference wire and another is an experimental wire. We'll have to attach the weight on the experimental wire to produce the strain. The Searle's apparatus does actually work on Hooke's law. The stress applied is directly proportional to the strain produced. So in this experiment, we can say that the wire extension is proportional to the weight we will attach to the experimental wire. Now if this is a wire of length L and cross-sectional area A, we are applying a downward force mg on the wire. It will get stretched little bit as per the weight we have applied, and so the length will increase. We'll say it delta L or small l given here. Normal stress is defined as deforming force F upon cross-sectional area A, and strain is defined as change in length delta L upon original length L. As Hooke's law say that stress is proportional to the strain by calling y as the proportionality constant, which we know as Young's modulus, y equals to longitudinal stress upon longitudinal strain, which is equals to mg upon pi r square upon delta L upon L. Now here is the procedure part given for both real and virtual lab. You can refer the procedure here. In this experiment, to find the radius of the wire, we'll use the screw gauge. If you don't know how to take the readings with the help of screw gauge, you can refer to the screw gauge video at OLAB first. Now this is the observation table and calculation part, which will be explained along with the simulation part.
Okay, now we are going to perform this experiment virtually here at OLAB. So here, as you can see, whole setup of this experiment is provided on the screen. Let us start performing this experiment. First of all, we have to set the value of gravitational acceleration, which is given here at top left part. Here it's already selected 9.8 as default. We will select the default one only. Now we have to select material. Here we will perform this experiment for aluminium material, but you can choose any material. For wire radius, we need to find it with the screw gauge when we perform this in the lab, but right now you can just select it here. Here we are keeping it as 0.1 millimeter, and similarly we will keep the wire length as 0.5 meter. Here at OLAB you can select different values and perform this experiment. Now here we have to select the weight, which are given in kg. It is the weight that we will apply to the experiment wire. Initially we have 0 kg, which actually means first we have applied minor weight to both the wires, so the experiment and reference wire stays erect. Thus more the weight, more will be the extension in the wire. First we are going to take the readings for this loading part. Now we can see here a shell at the top. We have to bring this white line on the middle of the shell. For this, we have to use this arrow given at the bottom. As you can see, we have to move this shell in the right, so we will set it like this. Now as you can see, this line is in the middle of the shell. Thus the reading of the spirometer here will give us the length of extended wire. Similarly, we are gonna increase the weight of the load and we will get different values of x. Now repeat the same procedure while unloading the weights from the wire and similarly take the readings. Now we will learn how to take a reading in this experiment. Here for 0 kg, it already shows 42 on the horizontal scale, which actually means we have connected very minor weight to the wire. Therefore, it shows extension even at 0 kg. Now we will connect the load of 2 kg on the experimental wire using the slider given here. Then we will match this line and center of the shell using these arrows given below here. Now this line is in the middle of the shell. Here as you can see, we have covered 4 divisions on this vertical scale, and on the horizontal scale it shows 94, which means our final reading will be 4.94. Similarly, during unloading, we have removed 1.5 kg from 3.5 kg of total weight. And we will take the reading similarly. So for unloading part, we have covered 4 divisions on the vertical scale and it shows 94 on horizontal scale, which means our final reading will be y is equal to 4.94. Now, as you can see, we have got the values of x and y, and here is the mean value of x and y. The next thing is we need to find extension, which is change in length of wire when load was applied on it. We can get this value by subtracting the value when there was very minor or say 0 weight applied from respective z values. And now we can calculate Young's modulus using this formula.